My guest today is Professor Antonio Lieto, who is Assistant Professor of Computer Science at the University of Turin. His research focuses on artificial intelligence, human-machine interaction, and computational cognitive science. Welcome, Antonio.
So, hi, Gill. Thank you for the invitation.
Yeah, so thanks for doing this. So we want to talk about your book that just came out with a fascinating title, Cognitive Design for Artificial Mind. And before we get into the details of this, I have sort of a philosophical question for you. I was wondering about this for a while. So as humans, we have made a lot of tools. Maybe 500,000 years ago, we have rocks and sticks. Maybe more recently, we have the internal combustion engine. So we have made a lot of tools, including computers. Why do we try to assign intelligence to computers? We don't seem to do that to any other machine or tools that we have created so far. Why are computers so different?
Well, yeah, these are deep philosophical questions, but philosophical question. I'm not sure I have an answer, but the main reason, in my opinion, is that with computers you do a lot of more things with respect to the tools that we have built so far along our history. So, in particular, I mean, the tools that you were mentioning are able to do specific tasks, but with computers, I mean, we can use, let's say, a computer for doing a bunch of different things, for going into the moon or Mars, or for I don't know, doing simple arithmetic or algebraic calculations, or for I mean, really a lot of different things. And this is, let's say, a kind of common element that we have with our ability, not just, let's say, not just our as humans, but let's say with the ability that all the natural, let's say, systems have. So, in other words, the idea is that we are able to use within this kind of, let's say, compressed and constrained anatomical engine, a lot of different things. And in a similar way, we want to use computers, this kind of machines, in a sort of general purpose way, in a similar way as we humans are able to do, and or as other animals are able to do.
Yeah.
I mean, I'm not sure if this is a satisfactory answer.
No, that makes a lot of sense. So in some sense, what you're saying is that the general purpose nature of the computer, that we can do a lot of different things with it, and we can do a lot of different things with our brain too. And so sort of the general purpose nature of the machine that allowed us to really think about usefulness of computers very differently from other tools that we have made. And so I want to go into the book. So you start with sort of the history. You start off by saying cognitive science was original artificial intelligence. Computers have been with us for more than 100 years now in one form or the other. But cognitive science is somewhat of a recent discipline, isn't it?
Yeah, okay. So cognitive science is an umbrella term. It is an umbrella term that covers a lot of different disciplines, like artificial intelligence, linguistics, psychology, anthropology, philosophy, and neuroscience. This is the so-called cognitive hexagon, okay? Because this is the idea. And there are, of course, different connections between the different disciplines that I have mentioned so far. But let's say what is nowadays called cognitive science, that is a term pretty new, as you were mentioning, was already, let's say, in nuce in the cybernetic tradition. So cognitive science is the new, let's say, version of cybernetics, which on the other hand was already, let's say, on the market, let's say, since the late 40s of the last century, due to the work of Norbert Wiener. And in some sense, cybernetics was, let's say, the common ancestors of both, let's say, artificial intelligence, and on both, let's say, the symbolic tradition in artificial intelligence, and also the sub-symbolic or connectionist traditions in artificial intelligence. But all the methodological paradigm in today computational cognitive science is a derivation of the methodological apparatus coming from cybernetics, with some adjustments and deviations, of course, because there were some decades of studies and of results in the middle. But this is, let's say, the overall framework of cognitive science. And in the beginning of the book, I try to make it clear how, let's say, the purpose of, let's say, how the purpose of the original artificial intelligence, the original field of artificial intelligence, was very much aligned with one of, let's say, cognitive science, which is understanding how the mind, the brain, and intelligence, let's say, works in both, let's say, biological systems and non-biological ones, so including machines. Okay, and but let's say, from my historical perspective, starting from the late 80s of the last century, there was a sort of, let's say, distinction of the research agenda of these two sciences of the artificial. This is a term that was coined by Herbert Simon, which was one of the really pioneers of in the field of both, let's say, artificial intelligence and cognitive psychology, and try to, let's say, try to build together with his colleague Alan Newell the first AI system by taking inspiration from the kind of heuristics that we use in order to solve different classes of problems. So at the beginning, there was this very strong alignment. Then there are several reasons for that started to
diverge a little bit. Yeah. So you talk about sort of the heuristics and AI errors. And so even going back in time from the Dartmouth meeting that I believe was in the 1960s, right? Mid 1960s.
Yeah, it was 56. Yeah, 1956. Yeah.
1956. There was a time when we used to call it expert systems, really very much heuristics-driven aspects of using computers to make decisions. This brings some memory for me, Antonio. My thesis in the mid-80s was a heuristics-driven expert system for education, where we were trying to figure out graduate students, how do we create a heuristic of their cognitive bias by letting them play in a large design field and let them make mistakes, and from that mistakes we could garner what cognitive biases they may have. And so heuristics-driven expert systems have been there for a long time. And as you said, late 80s, there's a bit of a divergence in terms of artificial intelligence, more empirically driven. And is this where we make the distinction between sort of the functional and structural methodologies, or is the sort of the connectionism and the opposite of that?
No, I think that the distinction between structural and functional models that I draw at the beginning of the book starts already before, let's say, these before the 80s of the last century. So before this divergence, In particular, let's say in a nutshell, this distinction, as I try to make it clear in the book, is between, let's say, artificial models, artificial systems that have an explanatory role with respect to a natural system that is able to, let's say, do the same class of task, okay? This is the case of functionalist system. In general, in functionalist artificial system, there is only a surface resemblance of how the system is built and how the algorithms within the system are built with respect to the heuristics that humans or other animals use to solve the same kind of problems that also the system wants to use. And on the other hand, there are the structural systems, structuralist systems that have a more constrained resemblance with respect to the natural system that they want to, let's say, somehow replicate. Okay, in which they want to, let's say, solve the same class of problems that a natural system is able to solve. So, structural systems have an explanatory role back with respect to the natural system that are taken as a source of inspiration. Why? Because they are explicitly designed by taking into account, let's say, different types of constraints that allows you to interpret the output that is generated by the system. On the other hand, in functionalist systems, you only have let's say this system just share the same input-output specification with respect to the natural system that is able to make the same kind of, or to deal with the same kind of problems. But the way in which the output of these systems is generated has nothing to do with respect to, let's say, the mechanism that are used by the corresponding natural system that is also able to, let's say, obtain from an observer perspective, from an external perspective, the same kind of behavior. So this is the main distinction, and was already known in the field of, let's say, computational cognitive science and cognitive modeling.
Yeah, so let me see if I understand this, Antonio. So would it be correct in saying a functional system is sort of an engineering design? So we have an objective, we can make that objective through an engineering design, like an aircraft flying, but it has nothing to do with, let's say, a biological system like a bird, for example. Whereas a structural methodology and a structural system would be trying to replicate in some way what a biological system does, right? And so it's not just the output, it's also the process of reaching the output.
Yeah, that's right. But I mean, I would say that both this class of artificial systems are, let's say, the result of an engineering solution. Okay, so they are both the result of an engineering solution. But as you were mentioning, on one end, you do not take into account the way in which, let's say, a natural system is able to solve the same class of problem, and on the other hand, you, let's say, take care also of the processes that lead to a certain kind of output. And in general, I would say one of the main elements of divergence of artificial intelligence, of the artificial intelligence field in the last decades, is the focus on the functional side. Okay, so starting from the 80s, as I was mentioning, there was the AI field starting to focus on very narrow application, also with the scope of commercializing some of these applications. I mean, on our phone, we have nowadays a lot of, let's say, narrow AI systems that are able to do a plethora of different things, right? But I mean, on one end, this kind of divide et impera approach led to this to the emergence of this kind of let's say narrow and hyper specialized system On the other hand, there was, let's say, we lost somehow the big picture about studying and understanding what do we, I mean, what do we mean with artificial intelligence, and in particular also from a practical perspective, how can we actually integrate in an autonomous agent all these different kinds of AI which are specialized in very narrow domains. I think this is the one of the key points of the book. So if we want to integrate all these different types of hyper-specialized AI, which work very well in that domains, we need to somehow study a little bit the architectural commitments that biological systems that also show this general purpose capability have and have to face in order to integrate all these different faculties. This is one point. So this is an important point. But yeah, please go ahead.
Yeah. So two thoughts come to mind, Antonio. So going back to our original discussion, we use computers. We look at computers as sort of a general purpose system. So in the functional design world, when we create this hyper specialized products, they're not general purpose machines anymore. They are actually very much like a tool, like an internal combustion engine. And so in some sense, I think you talk about this, IBM Watson, Google's AlphaGo. These are all functional systems, highly super specialized functional systems, are really tools that does one thing. So we can't really categorize them as in the world of artificial intelligence the way that people think about AI, can we?
Okay, I agree. I agree with you. But I mean, I have nothing against these systems, which are, let's say, the state of the art of engineering that we have. So they are great tools, great AI systems. I would say that they are specialized AI systems. They are not really able to, let's say, generalize the kind of capability that they have achieved in specific fields in order to cover the wide range of, let's say, capabilities that we have in humans. And one of the reasons of this, let's say, lack of capability of transfer, or let's say, of transferring what they are able to do in one field of in another field, is due to the fact that what we know in the field of artificial intelligence and computer science in the last 40 years is that we can really, we do not have any kind of I don't know what to say. We do not have one winning method in the science of the artificial, because these tools that you were mentioning use different kinds of modeling paradigms. One use symbolic probabilistic engine, another one use deep learning and deep networks machines. But we, as humans, are able to, let's say, have this kind of capability by integrating exactly these two different kind of paradigms and these two different kinds of faculties that arise from this kind of integration. So again, the integrate. I mean, we should be able to integrate AlphaGo with Watson and more in order to, let's say, compare, in order to have a sort of human comparable intelligence in terms of AI. But we are not really there. And I think one of the reasons is due to this hyper specialization and this hyper, let's say, focus on very narrow functional systems in the current field of AI.
Yeah, and we have a recent example. I think you talk about this in the book, GPT-3. A lot of people have been talking about it. it is the latest iteration of a hyper specialized thing that is unable to learn anything new. And I was fascinated by this. The infrastructure required to house it, you can't even move it anymore. And so talk about rigid AI or specialized AI, it has to stay where it is, and it can only produce what it has learned so far.
Right. I mean, this is an enormous problem because, I mean, we as humans, but also other biological intelligent agents in this planet are able to, let's say, ontogenetically learn new tasks. So we build from the knowledge that we have at a given timestamp, and we build on this knowledge by having new experiences, by interacting with new agents, and so on and so forth. So let's say that the knowledge, so the learning part is really say something that follows our ontogenetic evolution, and this is something that you cannot really do in this kind of system. Also because they face the foundational problem of deep nets, which is catastrophic interference. So the fact that when you learn new knowledge, actually you override some of the previous knowledge that you had in this network. So there is also this foundational problem. But again, this is not a message against the connectionist and the deep learning world, because I really think that we need that part, because they have shown that they are better than any other kind of modeling paradigms in all the perceptual task. Okay, and we need the perceptual task, and we need to integrate the perceptual task in the kind of general agent that I was talking about. But we really need to find a way to combine the modeling paradigms that have been developed so far in quantity science, computational quantity science, and artificial intelligence in a non-ad hoc way. This is the point, because there is plenty in the literature of hybrid system trying to, let's say, combine this kind of, let's say, the approaches and the output of the, let's say, neural networks and connectionist architecture to more abstract level of representation. But in most of the times, this kind of integration is done ad hoc. And while this work for building functional system, this let's say is not really scientific. Is not really something that has a scientific interest.
Yeah. So on the structural design side, I want to get your perspective on this, Antonio. I know that people are fascinated by the human brain, neuroscientists and computer scientists included, but the humans are not necessarily good decision makers, especially in the presence of high uncertainty and lot of data. And so I'm perplexed by this desire to replicate the human brain in domains that requires decision making in the presence of uncertainty. For instance, in the mid-90s, we demonstrated in a pharmaceutical company that machines can make a lot better decisions than senior managers. And so we know that humans are not that good. And so I wonder from the structural design perspective where that is heading.
Okay, so the fact that humans are not optimal decision makers is well known. And this, again, goes back to the study of Herbert Simon that introduced the notion of bounded rationality. So we are bounded rational agents because we have a lot of cognitive and biological also constraints that we have to face when we have to make decisions in an uncertain environment with incomplete information and so on and so forth. But another point of, let's say, the other side of the coin of the bounded rationality is the notion of satisficing. So even if we are, let's say, suboptimal in specific tasks, in general, we are able to, we are satisficing decision makers if we consider the whole spectrum of cognitive faculties that we are able to deal with this kind of, let's say, very limited very limited, and I would say low energy consumption engine that we have. So this is one point. The other point is that from an evolutionary perspective, the satisficing heuristics that we use are in most of the cases very useful to make fast decisions in an uncertain environment. Okay, there is a lot of discussion about whether all the cognitive biases that are known in the humans are really biases or they are heuristics, they are shortcuts. And there are many experiments showing how, in fact, they are actually heuristics, because in most of the cases, these actual, let's say, errors are the things that allows us to reason in a fast way in an uncertain environment, and that allows us also to make revisions in real time to the kind of decision that we have taken, let's say, 1 second before, and so on and so forth. So this is why it is important also in the context of AI, not just in the context of cognitive modeling, to pursue this structural approach, because most of, let's say, the biases are actually, most of our, let's say, weaknesses are also in a general setting our points of strengths. Okay, so if we want to integrate all the different kinds of let's say, capabilities that or even a part of the capabilities that we are able to show and to exhibit as intelligent human beings, then we have to really find a way to build a, let's say, satisfying overarching architecture that allows us to really integrate, let's say, all these kind of faculties. So we need to be suboptimal in a certain sense, suboptimal in the specific fields, but in general we need to be able to do many different kinds of we really need to be able to do many different kinds of tasks. This is the idea, and this is also the call for let's say to join the forces in the context of the cognitive architectures enterprise, which is also, let's say, an area in which I spend some of the time in the book, because this is also an old idea, but now it seems that we have, let's say, a major technology to really try to make this integration effort possible. The idea goes back to Alan Newell, to the early 90s, but now the community of cognitive architectures is really growing.
So I have a little bit of a bias here, Antonio, so I just want to get your perspective. I'm not sure humans are satisfactory decision makers in many domains. I'll just give you some examples. Financial markets, trading, for example. We can demonstrably show machines are a lot better than a human sitting in front of a computer and making trading decisions. And this is because we don't have stable heuristics, we have high uncertainty, 500,000 years of evolution. Heuristic generation, I agree with you that it's low power, it's very flexible, but it also requires heuristics that are necessarily stable. And so when you go to sort of scientific experiments that generates a lot of data, like the Large Hadron Collider, for instance, or financial markets, or in many cases, business decision making that requires a lot of data. Humans don't make satisfactory decisions. They make actually the wrong decisions. And so in some sense, I wonder from a design perspective, this idea that we should really take the human brain as a model is the right idea.
Okay, the point is this one. I'm using satisfying in the Herbert Simon terms. Okay, so even a bad decision can be satisfactory because this kind of heuristics is used in a suboptimal way in a variety of fields. So let's say this is an important point. I'll give you an example. Let us consider a quite well-known fallacy, which is called the conjunction fallacy. Okay, so the conjunction fallacy is a fallacy where, for example, I ask you to categorize an instance that I call Linda by saying, okay, look, Linda was a girl in the 70s. She was a green activist, and she majored. She had a PhD in I don't know, philosophy in the 70s, and so on and so forth. And based on this kind of, let's say, cues that I'm giving to you, I ask you to categorize Linda in this way by saying, okay, look, give these cues. Would you say that Linda is a bank teller, or that Linda is a bank teller and a feminist? If you have to answer to this question in a matter of few seconds, most of the people heuristically respond, okay, well, Linda is a feminist and a bank teller. Why? Because some of the cues prompted that kind of answer, even if it is obviously wrong from the point of view of a theory of probability. Because the probability of a conjunction is, of course, minor with respect to the probability that only one of the conjunctive elements is true, right? So this is classical probabilistic theory. But if I change this example in the following one, and okay, let's imagine that I'm walking into the mountain, and suddenly I see, let's say, a strange shadow, and I start what it is, and this item is 2 meters tall, and it weighs 300 kilos. It has, let's say, teeth which are very strong, and it looks very aggressive. What kind of decision should I make? So should I infer that this is a mammal, or should I infer this is a mammal and is also dangerous? So probably from an evolutionary point of view, it is better if I take the second choice, even if from a probabilistic point of view, it is still wrong, because it is exactly the same, the case of the conjunction fallacy. So this is let's say, an example. It is, of course, a toy example, but it is plenty of this kind of example of how satisfying heuristics is, let's say, is something which is built in our mind, because from an evolutionary point of view, having this kind of suboptimal decision strategies is really the best way to, I don't know, to survive to an environment in which we do not have complete information, and where we have to face with the uncertainty. So this is an example of satisfying heuristics. It is obviously wrong from the point of view of a theory of probability, but this is not really a bad decision. It is a good decision. It is better if I start running, if I see this kind of huge, let's say, Yeti-like thing, because most probably it is something that is dangerous for me, right? So this is just to give you an example about why it can be important to implement this kind of satisfying strategies within an artificial system.
Yeah, the problem though, Antonio, is that all those heuristics are based on 500,000 years. So we are a bit like fish out of water, right? Last 100 years, we have all this data. So if such a problem is presented, you say, well, I should run. Maybe in the modern world, I should take insurance, right? And so those heuristics that we hold close to our head, so to speak, are tried and tested heuristics for survival. But we don't have predators anymore. We don't really have any of those things going on. but we have, let's say, big data and we have uncertainty. How do we actually use those heuristics, or we cannot use those heuristics, but can we use the hardware that we have to these new problems? That is sort of a biological question, not just an artificial intelligence question, I think.
Yeah, I mean, it is right that we are probably, at least in, let's say, the most advanced countries, we do not have anymore this kind of problems, but still we have this kind of, let's say, primitive heuristic that move our decision making strategies. The point is that these heuristics are based on, let's say, some elements which are still there. So the fear, we still have fear in this world. The love, we still have love, motivation, goals. So we are, let's say, our decision-making strategies are really driven by a plethora of a variety of different things which are still there, even if, let's say, the triggers of these elements are not probably exactly the same of, let's say, some thousands of years ago. But still, also in the financial market, you can have fear of losing, let's say, your investment. So, which kind of decision should you make? I mean, and this goes on for all the kind of, let's say, the technologies that we nowadays use in our everyday life. So the driving elements of our decision-making strategies are still there, and it is again still possible that a machine in a, let's say, particular field makes a better decision than us. For example, they can make a better decision in the game of Go or in the game of Sudoku, okay, with respect to a human player. But I cannot play only Go or Sudoku. I can do a lot of different things, okay, by using, let's say, that minimal set of heuristics that allows me to, let's say, generalize and to, as we were mentioning, to use this kind of anatomical structure at a very, let's say, low rate of consumption energy in order to, let's say, to face the environment. So it is true that the context is changed, but the elements that drive our decisions are still there. And again, like in the case of the conjunction fallacy, in most of the cases, the use of, let's say, shortcuts, heuristics, can be a way to face the big data problem. Because, I mean, we are not able to really analyze big data. Of course, machines are better than humans and or than any other animal in analyzing big data. But the way in which we face that problem is by using these shortcuts. So, because while you are waiting that a computer is able to analyze all the big data, we have already done 10 moves, something like that, okay? Why? Because we are able to use the heuristics. So, and this is an important strategy from an evolutionary point of view. You cannot wait, let's say, for the entire, let's say, big data set being analyzed if you want to, let's say, have an agent that, for example, acts in the real world, that cooperates in a human with humans in the real world. That, for example, that cooperates with in the hospitals with in order to fight, let's say, these COVID pandemics and so on and so forth. So you cannot wait to analyze a huge amount of big data. I mean, our powerful, let's say, strategy is to use, let's say, few data, but having big models, okay? So if we have big models with few data, we are also able to, let's say, act and to, let's say, to react, I would say, to the kind of stimulus that we receive to the environment, in general, in a satisfying way.
So if I understand you correctly, Antonio, what you're saying is that the structural design paradigm is still very useful, and it is good to use the human brain as a model because it is flexible, it is generalizable, it's general purpose. Granted, its decision-making capabilities in specific cases are not optimum, but in general, it's able to do a lot of things reasonably okay, and hence that model is still a good one. So I want to go to another chapter in the book. A lot of people are, I mean, they've been talking about the singularity forever. I know that it's coming. I'm just convinced it's coming anytime soon. But suppose it's coming, and people have been talking about this in terms of how do we differentiate a human from a machine. There were very early attempts, right? There was a famous Turing test, and that is now, there are many iterations of it now, right? You want to talk a bit about that?
Yeah, I mean, the Turing test was, let's say, this idea of Alan Turing, where actually the behavior of a machine, the idea is that a machine is intelligent if the behavior, the output of a machine is not really recognizable by a human judge as different with respect to the kind of output that also a human can provide within a kind of conversation. Okay, a conversation in which, of course, the human judge do not know which is the kind of, I mean, who is providing the output that is reading. The problem of the Turing test, and this is something that is, let's say, explained in the chapter 5 of the book, is that this test is really language-based. And another problem, which is well known, is that it is, let's say, just based on the analysis of the output. But as I try to make it clear in the book, the same output can be generated by completely different mechanisms, by completely different processes. So what I propose in the book is another kind of, I would not say test, but it is a framework, an evaluation framework, which is non-subjective because, of course, in the Turing test, there are different judges that different human judges that can have different opinions about whether the output that they are reading is the one of a man or the output one of a machine or a human or a machine. Then another problem is that this kind of minimal cognitive grid allows for a graded evaluation. So in the Turing test, you have something like, okay, this is human and this is a machine. You have this kind of Boolean things. You do not you cannot really have, let's say, uncertainty in the kind of, as a human judge, in the way in which you judge the output of a given system. And in general, let's say, the kind of output that, the kind of framework that I proposed allows for both a quantitative and a qualitative analysis of the cognitive adequacy of the performances of the output of the artificial systems. Why? Because by providing this minimal cognitive grid, I consider three main, let's say, elements which are important. The first one is the functional structural ratio, because what I say is that the two paradigms that I have mentioned in the first chapters of the book, so functionalism and instructionalism, can be integrated, and they are actually integrated in a complex system. In a complex system, you cannot have an entirely structural system, because an entirely structural artificial system, because in this way, I mean, you go in what I call the Wiener paradox. So you should be able to replicate an entire human beings, okay, in computational terms, but this is, of course, not possible. So you need to find a balance between some components which are functionally integrated within a more complex picture, and some other components which are, let's say, more structurally connected with the way in which our brain or our, let's say, mind works. So this is the first element. The second element is the generality. So how this system is general and how this system can, let's say, how can we evaluate the intelligence of a system with respect to this generality issue that I was also talking about. And another point is the performance match, which includes not only, let's say, the same successful output, but also the errors. Okay, so an analysis of the errors that are produced by the system while the system is actually being used. Now, this framework is not language-based, can be used for language technologies, for embodied agents, and it provides a way to actually ground on a 2D space, okay, the different kinds of artificial system, cognitively inspired or not, or biologically inspired or not, that are developed in the context of both cognitive modeling and artificial intelligence. This, of course, cannot be done with the Turing test because, as I mentioned, it tests these problems. It is only based on the behavior, on the manifest behavior that can be obtained in different ways. It is only based on the language, but we use a variety of different kinds of other faculties in order to judge the intelligence of, for example, another human beings. And then it is, let's say, subjective, because different humans judge can, let's say, have different opinions about the behavior of about the output that they judge of the system that is going to be tested. And this is, of course, a problem of the Turing test. And I also reviewed the problems of other tests of intelligence, like the Winograd schema challenge or the newer theory of cognition. And I try to show how the minimal cognitive grid is a more comprehensive framework in order to, let's say, make progress in this kind of, let's say, evaluation effort. If you want to compare, let's say, the output of a machine with the kind of, let's say, output that we are also able to provide as humans.
Yeah, it's interesting. A more sophisticated test or a more sophisticated framework, like the one that you're describing, also can push the field forward, right? If you have a more sophisticated way to test something, then you can try to go further. So I think we are reaching a point. These types of frameworks are now needed to push the field forward. So I want to finish up with your thoughts on where the field is heading. So if you sort of look forward 5-10 years, let me ask you the the question of singularity. Do you think let me ask you in two different ways. Do you think we will ever reach singularity, meaning we are going to be completely fooled by a machine? And if we do, when do you think that is likely to come?
Okay, so I will answer to the second question before. I don't think it is coming, this problem, anytime soon, because as I try to make it clear in the book, the field of artificial intelligence, despite the huge progresses that has done, is really, let's say, galaxies away from the kind of abilities that we have, not just as humans, but in general, from the kind of abilities that animals or also small rodents have, okay, in order to survive, let's say, within our real environment. Then about the singularity, I think this is more something related to science fiction than to science. So I'm not really a science fiction expert. I think that as a scientist, we should really try to, a goal that we have to put in our agenda is to really try to have integrated systems. So integrated system in a non-ad hoc way that can shed light on also on some of the things that we think we know about the brain and about the mind, but that we don't actually know. So I think this is really a key research point in the agenda, at least for the perspective of the cognitive inspired and biological inspired AI. And I think that this is also going to be one of the goal of the artificial intelligence in general, because we are now reaching a point that this is coming to become clear now, where okay, we need to find a way to go beyond deep learning. Deep learning is good, reinforcement learning is good, but we need to find really something more in order to make the next jump. And my proposal, which is not really a new proposal, so I'm just trying to make the point of returning to some of the early elements that were somehow neglected some in the last decades, but then can be really useful for the development of the next generation in the next generation AI systems.
Yeah, so for my own understanding, Antonio, what you're proposing is sort of an integrated approach. So we had some ideas early on, we abandoned them, we went to this deep learning route, and I heard somebody say the other day that there's nothing deep learning cannot solve, from a famous company in Silicon Valley. And so what you're suggesting is that may not be, most human predictions have been wrong, especially about the future. So that may not work. What you're saying is that there could be attributes that we abandoned from previous iterations that if we bring back to the current regime, we might have even more powerful ways to solve the AI problem.
Yeah, also because it is not true that with deep learning you can do everything. I mean, this belongs to the category of marketing, not to the category of, let's say, the scientific vocabulary. Because you cannot do everything with deep learning. You cannot do everything with reinforcement learning. I try to make it clear by showing which are the foundations. To make it clear at this point in the book, by trying to show which are the foundations of these different approaches that now are used every day, they say, in the current AI field. So you can do something with deep learning, something with reinforcement learning, something with probabilistic reasoning, something with logic, something. But we really need to find a way to unify all these things, because an interesting thing is that all these different, let's say, pieces of modeling paradigms that have been developed have been shown to be able to model different aspects of cognition, but no one of them is able to model all the aspects of cognition. So let's say integration is really the key point that we should target. I'm not, let's say, I do not like to respond to this kind of marketing claims. With deep learning you could do everything, because this is just false from a scientific point of view. Otherwise, I mean, everything will be solved, and we will not be here talking about the next generation of AI systems, right?
Excellent. Yeah, I agree. I completely agree. Excellent, Antonio. This has been great. Thanks so much for spending time with me. I just want to mention the name of the book, Cognitive Design for Artificial Mind. It gives a good background of history, a good background of the status quo, and possible new directions. So thanks again.
Thank you very much, Gill, for this invitation. It was really my pleasure.